some coding example. So we will use GitHub Copilot with VS Code to see if you can think of some programming assignment, then we can do that, or we can do something that I'm thinking right now. Do you have something in mind? Okay. So I will take one example of the kind of things that I do. So I hated Excel while making plots for my thesis or papers or whatever, right? So I these days I rely a lot on GitHub Copilot to plot graphs whenever I have to make some graphs, right? So we will do an exercise here. Let's see how it does. I'm not even sure what I'm going to ask it to do, but we'll create some sample file. We'll put some data in it. We will ask the model itself to put some data in it, and then we will ask it to write some script to make a plot for us. Oh, sorry. Yeah. So, okay. Actually, I'm not connected to network, which will be a problem. So let me connect to the network. 1 second. Sorry. Can I connect to the Wi-Fi here? Is there? But I don't have LAN cable in my Wi-Fi. Okay. CW1 or what? Caps. Dot EC or oh, let's see. Sorry. So, which one? Which one? Connect. Okay. Yes. And 726. Okay. Yeah. So I've created a file, CSV file. Let's ask the model itself to put some data in it. So so this has given me some data, and then we can ask it to make a plot of based on the data. Right? Let's say plot of py. Let's say year on the x-axis and I'm getting some error here. Let's ask it to fix this error itself. Yeah, so this is doing something, this is plotting something, but it's showing a horizontal line. I'm not sure this is aligned with the data. As you can see, I'm totally unprepared for this demo. So this is not going well. So maybe it's better to just move on, but the basic idea is that you can ask it to do something and it can do something. And if it's not doing something, you can talk to it again, telling what is going wrong and it can fix it. So in this example, when I ran it for the first time, there was some error. Then I just feed the error back to the model and it is able to fix that error. Right? And we can do this. Ultimately, we can get to the plot. Right? And this is very, very useful for coding and many other tasks. And this talk is going to be about how these models work in the backend. How do they process your query? How do they generate the output? And what kind of inefficiencies lie in the processing of these large language models and what can we do to optimize them. So let's go back to the talk. Right? So large language models, or LLMs as we call them, they are AI models that can understand and generate language. In fact, these AI models have gone beyond language now. Like this field is making progress at a tremendous pace. So they can process language as efficiently as they can process images, for example, audio, video, and uh, yeah. So they can understand multiple modalities. What makes them work is the fact that they are trained on massive data sets. Everything available on the internet has been fed into these models plus much more, right? So they have been trained on a large corpus of data and they somehow are able to compress the knowledge of the world in in model parameters, right? And so when you feed in some input to them, they are able to understand what you are trying to say and they can uh, generate the output, like whatever you are asking them to do. For example, they can do language translation, converting, let's say, Hindi to English, summarization, conversation, and code generation. These are some of the examples that where LLMs have made tremendous progress. And in many of these tasks, they can do as well as humans, sometimes better than humans, right? And this is the basic architecture of a large language models. All of these follow similar architectures. There are some minor changes going from one model to the other, but primarily this is the foundational building block, which was originally proposed in a paper in 2017. Attention is all you need. And what you see here on the right is one block of the model. This is the decoder block. There are some operations here: layer norm, self attention, layer norm, and FFN again. FFN is the feed forward network. From a computational point of view, there are two interesting operations here. One is the self attention. Self attention allows the model to learn the relationship of different segments of the input with each other. That's the primary task of self attention. Feed forward network is another important component which helps it understand complex patterns in the data. Then there are layer norms and these residual connections. We can ignore them for now because these are not interesting enough from a systems point of view. They can be computed efficiently, and so we will ignore that. Right? So an LLM replicates this model multiple times. if you have heard of GPT-3, GPT-3 has 96 of these layers, right? And the output of one decoder flow goes to the next one and so on. The way a given piece of, let's say, text is processed is that there is something called as tokens. Like tokens are the basic units of computation for a language model. So for example, ECE at Indian Institute of Science, it will be represented as a set of tokens. A token can be a word, it can be a subword. This is fixed. Like when the model is trained, it is trained on a particular vocabulary of tokens. And there can be, let's say, on the order of 100,000 tokens that a model understands. So the given input is segmented into these tokens. Each of these tokens internally is going to get represented by a vector, right? So these vectors are what we feed to the model. And what the model produces at the end is also these vectors. And let's say for an end application, we can convert these vectors back to these tokens and send them to the user. So this is how LLMs process input and generate output. Right? And the basic property is that they predict one token at a time. You can feed them any number of tokens in a prompt, depending, there are limitations of the model, we can ignore them for now. But the output that they generate is going to be one token at a time. And this is going to be key. In fact, I mean, a lot of inefficiencies in the processing of large language models come from the fact that they are able to produce only one token at a time. And some examples to show why, like how popular these are and how like at what scale they are going to get deployed, right? So ChatGPT, for example, was the fastest growing application in the history to reach to hundreds of millions of users, right? And some reports say that the spending by all these major cloud providers like Microsoft, Google, Amazon, Meta, for example, combined together, the more than $1 trillion are going to get spent on building the AI infrastructure for large language models. Right? So these are becoming very, very important, and they're very, very expensive. So it's important for us to optimize their performance. Right. Right. So given this context, this talk is going to be, I'm going to go through these following points. Like one is I will introduce what is LLM inference, basically how these models are served. From a scheduling point of view, what are the goals and challenges? How current systems schedule different requests of different users, right? And then I'm going to particularly focus on a work that we have recently done called as Sarathi-Serve, where we try to optimize the scheduling of these language models. Finally, I'll conclude, and if there is time, then I can talk about some other things as well. Let's see. So the way inference works, right? So when I'm talking to the model, as I was feeding some prompts to GitHub Copilot, the way it works is that the model is running somewhere on some GPUs, right? There are some pre-trained weights of the model that reside on the GPU. This is the architecture of the model, right? So let's say this is one model that is running on one or more GPUs. The prompt, user will send a prompt, right? So for example, here the prompt is, how can we transform Mars into a habitable planet, right? What happens is the prompt goes into the model at once. So this will be tokenized, all the tokens will be sent at once. The model will process and it will generate one output token, right? So let's say simple is the first output token for this prompt that this model is generating. What happens after that is an autoregressive processing where the model is going to generate one token at a time. And so basically, once we get the first output token, let's say simple, we feed this token back into the model. There is something called as KV cache here. This is a state that the model is going to maintain for each request. This state is just holding the activations of all the tokens that it has seen so far for all the requests. So basically, when the model predicts one token at a time, which token will be produced depends on all the models in that sequence so far. Right? So generation of a token needs some information about all the prior tokens that are present in that request, and that information is stored in the KV cache. Right? So in autoregressive processing, what happens is that the model generates one token, you feed it back to the model along with the KV cache, which is the activations of all the tokens in that request so far. So, and depending on what you have in your KV cache and what is the current token, the model will just think of this like auto-completion, right? It will try to auto-complete this sequence and it will go on till the model says that this is the output, like the model will stop at some point. So this is the inference process. And so you can see here there are two clearly different phases here. One is the prefill phase where the prompt is processed. And the second phase, we call it the decode phase, where the model is processing one token and generating the next token. Right? So these are the two phases in inference that are quite different from each other. Right. So if you look at the lifetime of a request, it is going to be split into two phases. One is prefill, and then there will be a sequence of decodes. Right? The prefill phase processes these tokens in parallel. The decode phase processes one token at a time per request. Right? And I'm stressing here because this is what determines how well you are able to utilize your resources, for example, GPUs. Right? So parallel processing versus one token at a time has a clear implication on the system performance. So because prefill is processing lots of tokens in parallel, this is compute bound. And for something like GPUs, this is really good. Like they can compute this phase very efficiently. Decodes are memory bound, right? And because there are not many tokens getting processed in the decode phase, but for each token, you still have to read all the weights of the model. Let's say if the model is 1 trillion parameters, right? So this is 2 terabyte of memory. To generate one token, you have to read all those 2 terabytes of memory. Right? So this makes decoding memory bound, which is not very efficient because you are bottlenecked on reading data from memory. Let's go one level deeper as to how this actually works. Right? So here I'm taking an example of the prefill phase where there are two requests. One is the same request that we saw before. There is one more asking it to explain the theory of relativity and so on. Right? So as I said before, right, these tokens, these input strings are going to get tokenized. So think of this particular block as token embeddings of this input prompt. Right? So let's say how can Mars, all of these are individual tokens. Each of them is a vector, so together they form a matrix. And similarly, the second prompt is also going to get tokenized, and this is another token embedding matrix. Right? And these are model weights here, right? But when you go to the decode phase, you only have very few embeddings, right? Which you need to multiply with the same amount of model weights, right? And you continue doing this for each token for these requests. Now let's go one level deep again to see how actually it works on the GPU. How do we do these computations on the GPU? So these are the token embeddings that we have from these given prompts, right? These are model weights. We are going to multiply this matrix with the model weight matrix, right? But we don't multiply full matrix at a time. We actually do tile-based computation. So what we are going to do is we will split our matrix into smaller portions called as tiles, and we will load one tile at a time to do the computation. Right? And we do this tiling because there is something called as GPU cache, which is much more, this gives you low latency, higher bandwidth than accessing the DRAM. So we want to avoid going to GPU DRAM, which is much slower than computation. So we want to avoid going to them. So that's why we try to do maximum computation while accessing the cache itself. Right? And tiling helps us do that more efficiently. Once we load the tile, we don't have to touch the memory. We can compute within the cache itself. Now, the primary difference between prefill and decode is that when I'm loading these tiles, right? Once I load a tile for a given element of the weight matrix of the model, I have enough input elements to compute over. So the cost of reading these model weights from DRAM into cache gets amortized because I'm doing computation multiple times over each element of the weight matrix. So there is a high degree of data reuse in the caches. Enough input elements to multiply the weight matrix with, right? So the amount of computation is very small, and this makes this reading of data from GPU DRAM into caches the main bottleneck in terms of performance. You are not doing a lot of compute. So GPU cores, which we have like thousands of cores per GPU, they are sitting idle because the data is not available in the cache. We have to read it from DRAM, right? So when the request processing begins, prefill make good use of GPUs, but the decodes do not make good use of GPUs. No, actually the opposite. So processing, you always process only one token. Previous one has gone into the KV cache, right? Yes, yes. So computation wise, you are only processing one token. Yes, that we will. Yes, 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 yes. So absolutely correct. So the main, the simplest thing and the most obvious thing that you should do to improve the efficiency is to batch multiple prompts together and process them at the same time. It helps you avoid this bottleneck, but I'll come to what kind of problems that brings. It's slightly non-trivial for LLMs. In fact, that is the main problem that we are targeting in our work, right? So prefill versus decode, I will keep saying them again and again to drive the point home, but prefill is compute bound, memory is decode bound, right? What does this mean? So, right. So what does it mean to be compute bound and memory bound? Obviously, performance wise, one is good, one is bad. There are other implications here. Right? So here I'm going to take an example of one single prompt. This is the prefill phase, right? And on the x-axis here, we are going to vary the number of tokens in the prompt. So think of it like towards the left, the prompt is small, towards the right, the prompt is bigger, right? And there are two plots here. I'm going to show the latency of processing that prompt on the left plot, and on the right plot, we are going to show the system throughput, like how many tokens the system can process per second, right? Now, prefill phase is parallel and it is efficient. Efficient means that it can operate near the peak performance of the GPU, right? If you have good enough number of tokens in the and beyond a certain point, you are able to saturate the GPU so well that if the prompt gets bigger, the latency is going to increase, right? So for example, let's say my GPU can process 500 tokens per second at its peak performance, right? Then if the prompt is, let's say 256 tokens, those 256 tokens are also going to get processed in roughly 1 second. But when I go from 512 to 1000, because the GPU can process only 500 tokens per second, it is going to take 2 seconds for a prompt with 1000 tokens. So once you have saturated the GPU, in this example, we have saturated the GPU at 512. After that, latency is going to increase. In terms of throughput, the behavior is different. At 512, we have reached near peak performance of the GPU. So beyond that point, feeding larger prompts is not going to help improve performance. So throughput is maximized at around 512. I can process per second, yes. Right. Okay. So just remember this, that in the prefill phase, because it is compute bound able to use GPUs efficiently, increasing the size of the prompt is going to increase the latency. It's not going to increase the throughput. Right. Yes. Right. Right. Yes. Yes. Exactly. So, right. Okay. Now the decode phase is the exact opposite. So if we look at the throughput and latency of the decode phase, this is going to be entirely opposite of the prefill, that increasing the batch size. So I'm referring to the size of the input during decode as batch size, because a request can have only one token. So the way to feed more tokens is to increase the number of requests that you are processing, right? So this is going to be memory bound, not so efficient. So increasing the batch size is not going to increase the latency, it is going to increase the throughput. So the same point I'm making some redundant statement here, but it actually helps understand what we are going to deal with next. Right. 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 Yes. Right. Yes. Yes, so this is linearly increasing. Sorry, so there is some mistake here. Yeah, I think there is some mistake here. 16 to 32 is linear. I think 8 is some not correct. This value is not correct, but it is expected to be linear. At least till certain point, it will be linear. After that, it will kind of flatten for some reason. Yes. So still something like under 50 batch size, it increases linearly. After that also it increases, but not as slows down. Right. Yes. So good question. So if you see here, what happens during decode, we the most of the time goes in loading this model weight, this tile into the cache. Right? Computation is not much. If I have more tokens here to process, right? Because my bottleneck is transferring this segment of model weights into cache, there is not much compute happening. Once I have transferred it, I can do more computation in the same amount of time. Right? Right. Right. Uh, right. Yes, but when you do decode, so there are two computations that I initially refer to: attention and FFNs. Right? Attention starts becoming bottleneck at large batch size during decode, and it does not batch efficiently. So when you batch attention, two requests are going to take double the time of a single request. So the primary difference is uh, when we this picture is showing FFN computation. That is the feed forward network where you have model weights, you multiply them with the input. In attention, there are no model weights. During attention, the computation is between the token embedding and the KV cache of that request. So different requests do not share something. Refill generates KV cache. Yes. Right. Right. Correct. Correct. So again, prefill and FFNs, right? During FFNs, your input in decode input is small and prefill has large input, right? That is the difference in FFN. During attention, prefill is compute bound because you are multiplying large inputs. You have two matrix multiplications in attention, and during prefill, all of them are parallel enough. In decode, you are computing one token, but one token attends to thousands of other tokens in the same request. During prefill, 1000 tokens attend to 1000 tokens. So the amount of parallelism you get there is much higher than the decode. Right. Right. So this is same thing like prefill having more parallelism, decode not having so much parallelism. So tokens are bigger than the model weights. They can be like if you have like let's say if you are somehow able to batch 10,000 requests, right? Then because model weights, when we say like let's say 8 billion parameter model, 8 billion are not concentrated into one matrix, right? There are multiple layers. So 8 billion is distributed across multiple layers. So each of these will be hundreds of megabytes, right? And activations can be more than that if you are processing many requests. Right. Even though for each of these 10,000 requests, prompts, right? You still have to go and fetch old stuff and recache for the number of output will be generated so far. Yes. Yes. And that's what is killing. That is what kills. Yes, exactly. right? So maybe a better way to answer your question is like, why does the latency not increase during decoding? So there are two tokens that we are processing here, right? But the GPU has thousands of cores, right? And so during two tokens, we are using only some of the cores. If I could have bigger inputs here, I can do those computations on other cores that are currently idle, right? So whether I process two tokens or 10 tokens, they are going to take the same latency because the rest of the tokens will be processed on a different set of cores, right? Yes, yes. KB does not require model weights. So there is no model weights in attention. Attention is between the tokens of a given sequence, only between the token embeddings. But during prefill, it is parallel. During decoding, one token computes over 10,000 tokens. That compute wise, it is very little compared to how much memory you have to read. Right. So prefill increases latency beyond a certain point. Throughput does not increase. Decode exactly opposite now. Right. Now, so then ideally when we want to, let's say, host a model and serve it, our goal is to provide maximum throughput and lowest latency. And that's what we want to achieve. So let's look at, and we will see how to get there. Let's see how do we quantify the performance of the system. So these are some of the latency metrics, like time to first token, for example. So when you submit a prompt and when you get the first output token back, what is the delay? That is time to first token. It's a very important metric. Uh, the second is time between tokens. So once you have entered the decode phase, then what is the time between each successive token? Right? So that is time between tokens, or TBT. User experience, because you are chatting with the model, or when I'm asking it to code something, I'm waiting for the response. So optimizing TBT is also important for user experience. Right. Okay. So scheduling delay is when you send a prompt, it may not immediately get scheduled on the system. You may be waiting in a queue because something else is going on. So yes, 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 right. But there may be, like, the system may not be able to provide you uniform value for each token. One token may come within 50 milliseconds of the previous token. The other token may come after 10 seconds. So what we mean by that, we want to optimize the latency of, like, let's say TBT. We want to make sure that between any two tokens, there is not a big delay. It should be a fairly smooth streaming. Yes, I'll come to that. Right. So we want to minimize both of these, time to first token, time between tokens, to improve user experience. But at the same time, we want to service the maximum load that we can, because this is a throughput metric, serving capacity. Like how many requests can I process per second, for example, while meeting certain targets on TTFT and TBT. Let's say my target can be, I want to provide first token back to the user within 2 seconds, and successive tokens, they should not take more than 100 milliseconds each. We can define our latency targets in that sense. So once we have fixed the targets, then serving capacity measures how many requests per second can be processed. So we want to maximize serving capacity given certain targets on TTFT and TBT. This is our scheduling problem. And TBT particularly influences user behavior, so we are going to focus on that. Now I mentioned high throughput to be one of the scheduling objectives, right? And all along this, in this talk, we have been focusing on like batch size. Like decoding is memory bound, so we want to increase batch size to get through, I mean, gains in throughput, right? So batching is very, very important. I We cannot serve one user at a time on a GPU, right? We want to be able to serve multiple users at the same time. because that's how we can increase the throughput from the system's point of view. Now the challenge here is we want to, and particularly by batch size, we mean batch size during decode, because decode are mainly bottlenecked or memory. So we want to increase the decode batch size. But if you look at the timeline of a request, the first phase of processing for a request is the prefill phase, which takes, depending on the size of the prompt, it can take a long time, right? So between two tokens, if you have a new prefill coming in, then the inter-token, like TBT latency can become very high, right? So basically, when we want to serve multiple users on the system, we have to somehow interleave these prefills and decodes, right? Because without doing prefill, I cannot service a user. No, no, it's proportional to the number of tokens in the prompt. Depends. Padded, there is no padding. So if a prompt is short, it can be processed faster. If it is, yes, yes, we can start the decode. Right. So I'll come to that as well. We will see some like visuals of how prefills and decodes can get scheduled. But typically, to answer your question, we don't batch during prefill in general, because prefill single request can saturate the GPU, right? So batching will only increase your latency, right? So let's say two requests come in, right? Your request and let's say my request. Both of them are, if we schedule both of them at the same time, your request will take 1 second, my request will take 1 second, for example. But if we process them at the same time, your prefill will finish in 2 seconds and my prefill will finish in 2 seconds. Instead, if we schedule your prefill first, you can get the first token in 1 second. After that, my prefill can be scheduled and I'll get in another. So for me, latency will remain 2, but for you, it can be 1. Yes, so that is why TBT is a problem and we will solve that problem. That is the precise problem statement. Yes, yes, great question. We can do that. Yes, yes, yes. So I'll show some visuals and then maybe we can take some examples. Yes. So depending on the prompt, like if decodes are running with a long prompt, then the latency for that decode token depends on the size of the prompt. If a prompt is, people are going up to millions of tokens, but let's say 10,000 tokens, it can easily take like 2-3 seconds. Right. So basically we want to increase decode batch size, right, to get maximum throughput, but I have to compute prefills first. Without scheduling prefills, I cannot increase decode batch size. So batching system is going to have to do some interleaving of prefills and decodes on the GPU, and this scheduling problem essentially boils down to how to interleave prefills and decodes. A system that can do this efficiently will be able to perform better. So let's see how current systems do, and here we will see some schematics of how these systems like process do the interleaving of prefill and decode. So from left to right is the timeline of different requests. Let's say 3 requests are running here, A, B, and C, and the subscript D here denotes that they are in the decode phase. So we are generating their token. Now let's say here one iteration is finished, and what happens here is, say request C exits the system, it has completed, but 2 more requests arrive, D and E. Right? So you can think of A, B, C being different requests for different users. So 3 different users, they have been running for, let's say, for some time, all of them in their decode phase. Right? Prefill has finished. We will see how new prefills are rendered, right? So here C exits and 2 new prompts come in. Say from yes. Yeah. So then basically we are looking at the previous iteration. Yes. Yeah. Correct. Correct. Exactly. Right. So we can schedule prefill and decode anytime. We can schedule them together or separately. That is completely up to the system. Yes. Yes. So yes. We don't know how much they will take, but we know at every time like what is the state of memory. This you know, but you don't know how much that you do not know. That we do not know. If you start with the realize that I finished the entire leftover memory, but still it's not done. Yes. Then you have to preempt some of the requests and either start. They will not be happy, but that's a. That's what you do. That's what you do. Or you can build some higher level policies. Let's say people have done that. People are still doing that. You can try to predict what will be the length of each request and use that information to guide the scheduling. So try to avoid those situations where you run out of memory at a higher level. You can do that. Right. Yes, right. In general, we don't know, but you can build some simple models that with reasonable accuracy they can give. They can, with reasonable accuracy, they can predict. Input tokens are already known. If you show up, at least I would know how much I need. Yes. But if you have such a large request that I cannot even tell you. Yes. Then maybe you just wait, right? You just wait, yeah. At that point, you have to wait, or then you have to deal with like policies. For example, if it's a really, really important request, then you take some of them out and schedule the new request. All of that can be done at a higher level than these. But so this is going to show one timeline of one particular system that does prefill and decodes, interleaving of them in different systems will do it in different ways. So ABC are running, for example, C exits, two new requests come in D and E, and what the system has done is scheduled the prefill of D first and the prefill of E next. And during this time, these requests that were running A and B, sorry, you can do this, you can do D and E together, but they will still finish here because this is prefill parallel, so latency will increase, right? Throughput will not increase. That's what we saw. But I got the D and E. Yes. If that is the case, then you can batch, then you will get some efficiency. You can finish. Yes. If these are really small prompts, then you can. But if yes, important to know. Yes, yes, yes. They're important to know. So basically, two of them can finish here or here or here. I'm just taking an extreme example that both of them are able to saturate the GPU. So the benefit of, in this particular example, the benefit of scheduling them separately is that the output token of D gets generated here, so we can return it, right? So the TTFT, time to first token of request D, is at least low, right? So the user of this request may be happier, right? So yes. No. So prefill gives you the first output token. End of, yes, right, right. So D, the prefill of D is done here. Time to first token of D gets generated here. The first token of E gets generated here, and after that, both of them have entered their decoding stage, and we can continue running A and B and D and E. Right? Yes. Yes, we can do that. System logic for it. Yes. So the system logic is that whenever we run decode, we want to run decode with the maximum batch size. Oh, if the decode waiting enter. Yes. That is, so this is more of a system facing technique in the sense that anytime I do decode, I'm not able to utilize my GPU. No, my point is that I could have started decoding after the right. You could have done that here, right. And then you could have. That is another policy. Yes. Yes. So if you want to improve throughput, you want to make sure that you are running decode with the highest possible batch size, and that is what this particular strategy is doing. Right. Let's look at another strategy. So again, the same state, A, B, C running, C exits, two new requests arrive, right? What we have done here is that D and E, both of these new requests, their prefill is scheduled together with the ongoing decodes. And because there are two prefills in this particular state, it is going to take a long time. So no request is waiting there actually running, but latency will be higher.
This is AD&B. Now I'm not clear anymore that how many output tokens we have generated for A and B doing digital results. Right now you have some shared compute, right?
Yes.
Refill and
yes. 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 So there is some shared compute here, but whether that benefits or not depends on the sizes and all that. So I'm just abstracting it out to simplify the discussion into saying that this can take a long time because you have two prompts here. Both of them are compute bound. They are going to increase the latency. They may or may not be. So that just depends on the details, like what is the prompt sizes, context length of each request. This may be better than this in some cases, this may be better than this in some cases, that depends on it. But in general, the problem remains that latency is high. Now, we can do something else too, like we can build an arbitrary set of policies here. I'm giving some examples of how current systems are doing, or at least they were doing till 1 or 2 years back. Again, the same scheme, we started with ABD, C finished, D and E enter. But in this scheme, we are not going to admit D and E into the system. We are going to run A and B. So A finished here, we will continue to serve B. And only when A and B have finished, we are going to schedule the prefills of D and E. This can be one of these strategies. Good or bad, like that depends, because TBT in this case is, you are getting very low TBT, right? No request is waiting because some other request, some new request has arrived. Yes, they have to, yeah, it's worse for them, but good for TBT. So for the throughput from, yes, but if you care about TBT only, let's say, right? Nobody is using it. I mean, people were using it. They got replaced because some people came up with better strategies. But this gives you the lowest possible latency value for TBT, if that is what you want to optimize for. Right? So now we can kind of like categorize them into different buckets depending on what they are doing. So let's call them like, this is a prefill prioritizing schedule. In the sense that when new prefills come in D and D, they get immediately scheduled, right? And the decodes may or may not get scheduled together with them. That doesn't matter. But the key point is that prefills run as soon as they are available. Given that GPU memory is also available, but for this discussion, we will just assume we have enough memory. And the second class here at the bottom is the decode prioritizing schedule. Like if I have decodes to run, I will run decodes first, and only if there are no decodes, then I will schedule new prefills. Let's look at the pros and cons of these strategies. So this is a prefill, these two are prefill prioritizing. They increase your TBT latency because TBT of the ongoing requests A and B, they see interference because of new prefills. This strategy is optimal for TBT, but it's really bad because you are running decodes with low batch size, which is not good for system throughput. And in fact, for TTFT also, it's very bad because these requests have to wait. So let's kind of look at this this scheduling trade-off between throughput versus the latency. How are like different systems dealing with it? So the system that we see here, this strategy was done. This was followed in a system called as faster transformer. It was one of the first systems for LLM inference by NVIDIA. And these two strategies were proposed in some of the recent systems. So decode prioritizing schedules will give you very low TBT, but very low throughput, right? And some other strategies, like what we saw prefill prioritizing scheduling, these are two of the, let's say till 6 months back or so, they were the state of the art systems, or kind VLLM, they prioritize prefills. They give you very good throughput, but they do it at the cost of very high TBT latency. And there are some other systems that can do dynamic, that decide dynamically based on the state of the system, based on some heuristics, which one to prioritize. And they are somewhere in between, right? But none of these is ideal. An ideal scheduler should be somewhere here, right? Very high on throughput, but very low on latency. That's what we should strive to do. And we will see how we can build this ideal scheduler, right? So, and basically this was our search, like we were trying to do this, and to do this we proposed like Sarathi-Serve. There are two key techniques here that we will do, and I will show how these work. One is prefill chunking and one is stall-free batching. The idea behind prefill chunking is that one prompt, if you schedule the entire prompt at the same time, it is going to take a long time. So then decodes get delayed. What if we can split a prompt into multiple smaller chunks and process one chunk at a time? Then you can run decodes in between or along with these chunks. You can control the latency by chunking a prompt, right? And then use this to form stall-free batching where decodes never have to wait for prefills. Right.
So you're thinking that prompts as like multiple tokens.
Yes.
What do you thinking that like think of this as multiple prompts?
Yes. Yes.
Send first one.
Yes.
And then second, but you sort of need context. Right now you're sort of not worried about that.
No, we are worried about that. The good thing is we can do it. There are some technical details as to how we multiply. Right. They are not independent. They're not completely independent in the sense that when you do decode, right, you are processing a token that you have not processed before, but it needs to know the context of all the tokens in the history. The same thing happens with prefill chunking. When we schedule the second chunk, it needs to know the context of the first chunk, which is
backside the event for output token generation is actually taking context of everybody in there.
Yes.
They are finding unrelated things.
Yes. Right. The same thing. So the computation of every chunk.
I think that sort of trying to make all prompts of both sides.
Yes.
That's what it is.
Yes. Exactly.
The second one.
The second one is stall-free batching, that you schedule these chunks along with the decodes that are already running. So decodes never have to wait.
Now the question here is basically what is the impact of doing both of them together?
Yes. So I'll come to that. Throughput. Yes. Right. So this is what we saw. There is a notion of input tokens. It's just, so let's say if your prompt has 1,000 tokens, we can divide it into 10 chunks. Each chunk will have 100 tokens. Yes. Yes. Embedding is token wise. So if you have 100 chunks, each token has its own embedding, irrespective of chunking. Like each token always, like for the model, for the system, token doesn't mean anything. It's these embedding vectors that we have.
So the variability in token size is bad.
Yes. And chunking eliminates that. So chunking gives you two benefits. One is latency, right? So when a long prefill gets scheduled, for example, right, in this particular scheme, let's say decodes are waiting, like A and B are waiting for the prefill of D and E to finish. If you chunk and divide them, like if you process one chunk at a time and run decodes with them, decodes don't have to wait. This period, this wait time of A and B goes away. Right? After, yes. There is also throughput gain that I will come to that. But let's see. So this was a prefill prioritizing schedule that does D and E and then clubs everything together, forms a batch of 4 requests. What we do in Sarathi is that, let's say there is a new, let's say D prompt, right? So we are going to divide it into multiple chunks, like D and E, 2 prompts. We are going to create 2 chunks of these. So P1 and P2, like prefill chunk 1 and 2. And similarly, E is also going to get divided into 2 chunks. And the way we should schedule them is that A and B are in the decode phase. A and B will always run. But each time we are going to add 1 chunk in the schedule. Right? So D gets the prefill of D. Rather than computing it all at once, we are computing it over 2 iterations. Right? And in those 2 iterations, A and B continue to run. Similarly, for E, we computed the prefill over 2 iterations. All the decodes continue to run.
You say A, B, and B1, right?
Right.
So we prefill for the first chunk of D.
Yes.
And then the output. Now you could have started generating the output for D as well, right? A, B, B, and
not here. Like until the prefill gets completed.
Oh, you saying that unless the entire thing, you're not going to start output of the generation.
So both of the chunks have to complete.
You should know that's but you could have started, right?
No.
Unless the entire thing is done, you're not. Okay, but now if you put up an ADPD.
Yeah, so that's missing here. My mistake. It's actually ADPD and D also runs.
Yes.
So here decode batch size is, like I missed putting it here, but that is precisely what we do.
Still not answered that. Doing this,
I'll I'm just coming to that. I have some graphs to cover that point, right? So if you see here, like there are no stones for any of the requests, right? And chunking takes care of that. We could have started generating decodes for this D request here itself, but then we are changing the behavior of the model. As a systems optimization, you don't want to do that, and it leads to incorrect output because the first token, right? You need the yes, you need the entire context, and until you have processed all of them, it's wrong to start producing output. So actually, computationally, what happens is that we do get one output token, but we just discard it. It's not useful. Uh, I'm going to skip this. This is just a visualization of how this works, but hopefully this is clear. The important thing is that chunked prefills are functionally equivalent to a full prefill. So from the model output point of view, nothing changes. And if you look at where Sarathi-Serve fits in this scheme is somewhere over here. So it gives you high throughput and low latency because of these techniques. And basically what makes all of this work, and I'll come to the exact numbers in just the next slide, but what makes this work is a very, very fundamental performance analysis technique for systems like roofline, we call it roofline analysis, that tells you, like for a given algorithm or an implementation, what kind of performance you can expect depending on the arithmetic intensity of your algorithm or implementation. So arithmetic intensity is how much computation you are doing per byte of data you read from memory, right? So the amount of computation in prefill, because it processes lots of tokens in parallel, this arithmetic intensity for prefills is high. It's really, really low for decodes. So decodes fit somewhere here, very, very low arithmetic intensity. Your performance is very poor. Prefills operate somewhere here, where they are much beyond the knee point. Too many tokens getting processed, right? So you are already so at this point you have obtained peak performance, right? You are not going to increase your throughput. Only the latency is going to increase at that point. In Sarathi, what we try to do is operate at this point, where you have achieved peak performance or very close to peak performance, but without incurring the latency of like adding too many tokens. And this is one particular example of how these numbers look, right? So the x-axis here is showing how many tokens you are processing in the batch. This is sum of prefill and decode tokens, because in Sarathi we are scheduling them together, right? So this is the sum of prefill and decode tokens. This is latency on the y-axis here, and here there is throughput. So depending on the we profile a model based on this and see basically what should be the number of tokens where we achieve the knee point of this curve, right? So we profile it and we pick the point that we basically that we want to operate at, right? So here in this particular example, if you are processing 512 tokens, your latency is only slightly higher than one processing smaller set of tokens, but your throughput is very, very close to the peak throughput that you get, right? So then what we do in Sarathi-Serve is that every time we are scheduling maximum 512 tokens, and it allows you to operate near lowest latency and highest throughput. You can do them at the same time. And yeah, these are just some evaluation numbers for different models. Like one good, so the key benefit of Sarathi is that you are able to increase batch size to as high a value as you can without ever posing any request. Right? Because when a new prefill comes in, we are processing only one chunk at a time. So no request has to wait. So we can reach the highest possible batch size without compromising on latency too. That is the main benefit. And this graph is showing that you can service like 4 to 6x higher throughput than the systems that were doing before us. And another thing that you can do is like we are showing here, like SLO is service level objectives. These are like latency targets. S and R denote like strict latency target or relaxed latency target. The benefit with Sarathi that we have is that depending on what kind of latency we want to operate with, we can tune the chunk size accordingly. If you want to have very low TBT, we can reduce the chunk size successively. If we can tolerate some higher latency, we can operate with a higher chunk size. There is a trade-off involved there, but can be controlled depending on what we want to achieve. And finally, this is summarizing what we have. Like scheduling is an interesting problem for LLM. You want to achieve both high throughput, low latency, which was not possible in previous systems. And with two really simple techniques to actually, we are able to deliver both. And this was simple enough that most of the serving systems today have actually adopted these techniques, and LLMs are served with these techniques. Right. I think I've taken more time, but we can stop here. Any more questions? Yes. 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 No. 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 For a given model and hardware, the number will be different. But it's easy to profile. Like it takes hardly 1 minute to profile that, and you can figure it out fairly easily. So, what factors influence this? Right. One is your GPU specifications, like what is the ratio between GPU's compute throughput versus memory throughput. That is one factor. The second factor is the size of these matrix multiplication. That depends on your model. Right? So if you're embedding vectors, let's say each vector is of, let's say 4,000, like dimension. Right? That may have a different profile. If your hidden size in the model is, let's say 8,000 or 12,000, then higher hidden size means smaller inputs can be computed more efficiently. But in general, yeah, it depends on the model and hardware specification together. And also model can be deployed in multiple ways. Like you can put it on one GPU or you can distribute the same model across multiple GPUs. It's a complicated answer. Like parallelization strategies also make a difference. So you profile and figure out, and then you basically start serving. That's the thank you. Thank you.